Hello student, I welcome to the video lecture series of Introduction to MEMS. The topic is bulk micromachining. So before I start the bulk micromachining, I just introduce what is MEMS. The full form of MEMS is micro electromechanical systems, and in MEMS we need lot of microstructure like flexure, cantilever, membrane, nozzle and many other structure which may be symmetric or asymmetric. But to get those structure in MEMS technology, we may see material like silicon, quartz and many other material using certain technique which are compatible with the VLSI process. And those technique are mainly the etching technique, and in particular anisotropic etching technique is used for making microstructures in MEMS. Now micromachining is defined to be a process of shaping silicon or other material to realize 3D mechanical structure, moving or static, in a miniature form. Micromachining has become a dominant and fundamental technology in the fabrication of microsensors, micro-actuators and microstructures. So now there are two kinds of silicon micromachining. One is called bulk micromachining and other is known as the surface micromachining. So in bulk micromachining, it means the whole silicon crystal or bulk silicon crystal we want to machine and we want to have certain microstructure. On the other hand, surface micromachining means on the surface of the silicon wafer you want to have certain microstructures, not the whole bulk material is used. So obviously the surface micromachining microstructure is much more sophisticated and much more attention is required. But in bulk micromachining, the structure are heavy and you can have the larger structure, heavier structure. By etching complete bulk solution, you can get the structure in the case of bulk micromachining. Micromachining is an important class of MEMS process. In bulk micromachining process, a portion of the substrate or bulk is removed in order to create freestanding mechanical structures such as beams and membranes, or unique three-dimensional features such as cantilever through the wafer's hole. Bulk micromachining can be applied to a silicon glass, gallium arsenide and other material of interest. Here we are focused on bulk micromachining of silicon substrate. There are two categories or two major category of process for bulk silicon etching according to the medium of the etchant, that is wet etching and dry etching. Wet silicon etching process used a liquid chemical solution in contact with silicon, and dry etching process used plasma, which is high energy gas content or containing ionized radicals, or vapor phase etchants or to remove materials. Silicon etching can be classified according to the three-dimensional distributions of etch rates and profiles of resultant microstructures. The etch rate of wet bulk etching may be depend on crystal orientation. The etch rate of dry bulk etching may be depends on direction in of wafer. If the etch rates in all directions are identical, the etching is said to be isotropic. If the etch rate is orientation dependent, the etching is said to be anisotropic. Three planes are shown in this presentation, that is 100 plane, 110 plane and 111 plane. The technology for silicon anisotropic wet etching has been developed over the past 20 years. It is a versatile process and can be used to create pieces structure. The process has been used to successfully fabricate many commercial products including silicon pressure sensors, accelerometer, and scanning probes microscopes. Today, new processes are being developed to supplement and replace the silicon anisotropic etching. The deep reactive ions etching process, for example, offer high vertical aspect ratio, unique vertical wall profile, and better material selectivity. New materials such as polymer substrate are being used for more frequently. This anisotropic etching process three-dimensional shapes from two-dimensional mask features. The three-dimension profile is made of bulk micromachining. The wet etchant for silicon and silicon compounds are HNA for isotropic etching at room temperatures, alkaline chemicals with pH is greater than 12 for anisotropic etching, and popular anisotropic etchants are KOH or potassium hydroxide, EDP, and tetramethylammonium hydroxide. These are the popular anisotropic etchants, and most of the etchants are used with ratio by weight 1:1 mixture with water. So here typical etching rates are for materials silicons 100, etchants are KOH or EDP, and etchant rate is 0.25 to 1.4 micrometer per minute. For EDP, the etch rates is 0.75 micrometer per minute. So same here, silicon dioxide when etchant is KOH, the etch rate is 40 to 80 nanometer per hour. So EDP also is there, 12 nanometer per hour, and silicon nitrate when etchant is KOH, 5 nanometer per hour, and EDP when silicon nitrate EDP is etchant used, that 6 nanometer per hour. So these are the different etchant rates and materials when we use for etching of bulk micromachining. Selectivity ratio of etchants. Silicon compounds are much stronger etching resistive material than silicon. This material can thus be used as a mask for etching of silicon substrate. The resistivity of etchant is measured by selectivity ratio of a material, and this selectivity ratio is defined by the etching rate of silicon by etching rate of the material using same etchants. So selectivity ratio of etchants of two silicon compound substrate is given in this table.